In this video, we're going to look at the dot product. So far, we've looked at adding two vectors together and multiplying a vector by a scalar. So now, is there a possibility way that we can multiply two vectors together? And that is what's known as the dot product. The dot product is going to give us a single number answer at the end, however. It's not going to give us a vector. So to do the dot product, you're going to multiply each of the terms. So A1 times B1, A2 times B2, and A3 times B3, and then you add those values together. So the dot product of A and B is what you see on your screen here. We looked at it in terms of a three-dimensional one. A two-dimensional one's the same thing. You just are going to actually do it based on the A1 and B1 and then A2 and B2. And that should be a times, not a plus on that slide there. So let's look at an example on how it's actually done. So we've got 2, 4, and 3, -1. So we do 2 times 3, and then 4 times -1, and we add those together, and you get 2. Notice it does come out to be a single number, not a vector. We look at the dimension one. We got -1 times 6, 7 times 2, and 4 times -1/2. Add those together, and we get 6. You also can do this based on the IJK setup of the vector. You're going to do the same thing. You're going to multiply the number in front of the I, so that in this case is 1. And notice there is no I in the second one, so it's 0. Then 2 times 2, the two numbers in front of the J's. And then -3 and -1, the numbers in front of the K's. And we get 7 for that one. The dot product has some basic properties, and most of these are very similar to the ones we use for regular numbers. A times A is just the distance of A squared. A times B, you can reverse it to do B times A. Or the dot product of A times B plus C, you're just going to distribute. So it's A times B, or the dot product of A and B, and then the dot product of A and C. If you have parentheses, we can shift those parentheses around. You can also shift the scalar value around as well. And if you multiply by 0, you're going to get 0. The next thing that we can use the dot product for is to actually help us figure out the angle between two vectors. So if you can see here, we have a geometric representation of the vector A and the vector B, and we have theta in between that. So if we look at the process to this, the formula for us doing this is the dot product of A and B equals the distance of A times the distance of B times cosine of theta. So if I know the angle and I know the distance of A and B, I can figure out the dot product of it. So if we look here, if the vectors A and B have lengths of 4 and 6, and the angle between them is pi over 3, we can use that to figure out the dot product. So we just multiply 4 times 3, and then the cosine of pi over 3 is 1/2. So the dot product is 12. The more useful case of this is the actual corollary to it, which is taking the cosine, is being able to figure out the angle between those two vectors. So if I know the dot product, I take the dot product and I divide it by the distance of A times the distance of B. And then I can use that with the arc cosine to find the angle. So if we look here, the first thing I have to figure out is my distance of each of the vectors. And we did that in the last exercise. We did, it's the square root of 2 squared plus 2 squared plus, or -1 squared, so the distance of A is 3, and the distance of B is the square root of 38. We then calculate the dot product, which in this case is 2. And we can plug that in, and then we do the arc cosine of that, and we can figure out that the angle between those two vectors is 84. One of the benefits of being able to figure out the angle between two vectors is to determine if they're perpendicular or orthogonal. If the angle between them is pi over 2, that means that they're perpendicular. So if I look at the theorem that we had just talked about to figure out with the dot product, we look at the distance from of A and the distance of B, and we multiply by the cosine of pi over 2. Cosine of pi over 2 is 0. So if two vectors are perpendicular, then the dot product will be 0. So if I come up with the dot product of 0, then I already know that those two vectors are perpendicular, and I don't have to do anything else with that, which is very useful when we're starting to do some real-life applications of our vectors. So let's look at an example that we're going to actually show that these two vectors are perpendicular. So I've got two 2 and negative 1, and then 5, negative 4, and 2. So I multiply those. So 2 times 5 is 10, 2 times negative 4 is negative 8, and negative 1 times 2 is negative 2. So that comes out to be 0. So those two vectors are perpendicular based on my previous statement. And it doesn't, when we're looking at those vectors, nothing in there tells us that they are perpendicular, but by being able to do the simple dot product, we are able to figure that out. So if cosine is greater than 0 and less than pi over 2, we get a positive angle. If it's 0, if it comes out to be pi over 2, then we get the 90 degrees. And if it's less than 0, we're going to get an angle that's obtuse, or bigger than 90 degrees. So by figuring out those dot products, we actually can start to determine what the angles are between those two vectors. There is also the extreme case where the actually comes out to be 1. So the cosine of theta equals 1. So the dot product equals the distance from of A and the distance of B. Then we have two vectors that are going in the exact same direction. If they're going in opposite directions, we are going to get negative 1. So they'll go in the opposite directions of those the vectors. So the last thing we're going to look at is direction angles and direction cosines. So the direction angles are going to tell me the angle of the vector as in relation to the x, y, and z axis. So to do this, we're going to use the corollary of 6 that we looked at before when we were looking at cosine of A equals the dot product of A and B over the distance of A times the distance of B. This is very similar to that. We're just going to look at it in terms of each of the components of the vector. So we're going to look at it A1, A2, and A3. When we're doing those, if we actually square each of those, you're going to see that it ends up equaling 1 at the end. So we can actually use those equations that we just looked at to write it as a vector, as the components of the vector. So A also equals the distance of A, and then the vector is the cosine of A, the cosine of B, and the cosine of Y. All right, let's look at an example. So we're looking for the direction angles of the vector A, and it's 1, 2, and 3. So the first thing I have to find out is my distance. So the distance of vector A is going to be the square root of 14. And then I just plug in the value of each of those, so the 1, 2, and 3, over the square root of 14, and then do the arc cosine. So it is a 74-degree angle to the x-axis, a 58-degree angle to the y-axis, and a 37-degree angle to the z-axis. So that gives me my angles to each of those respective axes.